One of the distributed energy resources available to us is thermal energy storage. And thermal energy storage is used in Ontario, and there are a lot of examples of thermal energy storage in Ontario. It's used to what I like to call peak shave, or to get rid of the demand at peak times of the day. So it is part of the peak demand response in Ontario. And the IESO can work with large commercial and industrial operations in order to see the benefit of thermal energy storage. So why would we be interested in thermal energy storage? Well, to reduce that peak helps us because some utilities offer rebates or rate incentives or take away any rate penalties if you are using your power off peak hours. So if we use our power, if we use our power off peak times, let's draw sort of a wintertime peak here, a wintertime peak for energy. And if this were time, then wintertime would kind of look like this. That, at 7 a.m., there would be a peak to try to, warm up houses and heat facilities. And then you kind of go out to work or run regular time. And then you would, or run regular production. But then people start getting home and they warm up their houses again. And it sort of goes like this, right? And then it's going to repeat like this again each day. So if you are asking for electricity right here at the peak time, then we have to run some gas plants right now. This is 2023. We have to run some gas plants in order to meet that peak. If we could make it so that we are always asking for this amount at this time of day, and we sort of ask for some more energy here, then our peak ends up, or our required capacity ends up, our demand ends up being here, right? So if our demand is level, then of course we can satisfy that with things like wind and solar and nuclear and hydro. Those level loads, we don't have to turn on gas plants, right? But for us, it's good for us because we can we will no longer be paying that peak demand charge to encourage us to behave in this manner that we like. We can also, using thermal energy storage is not really, it's a big investment, but it's not a huge investment. If you look at the size of large chillers, large boilers, you can buy smaller equipment if you have a thermal energy storage tank. Is also an advantage to thermal energy storage. Reliability, having the smaller equipment, smaller fans, smaller pumps that you're going to be running in order to run your systems if you have a chiller. So the payback time is usually, if we did sort of a simple payback, are usually around 5 to 7 years. If you look at the amount of demand power, peak power costs that you're going to be saving. Sometimes you could get in the 3 to 5 year range if you have existing chillers and boilers. All right. There are some paybacks that have been on the range of around 1 to 2 years for new construction altogether. All right. Okay, so a conventional air conditioning system, it's going to peak at cooling time, and it's going to be sized to meet those peak cooling loads. So a conventional air conditioning system, conventional air is going to run here, and it's going to cost a lot. It's going to have the lowest efficiency at the time when it's needed the most, and it's going to be sized to meet the peak cooling load, right? So conventional air conditioning. conventional air conditioning systems have a few drawbacks, and their drawbacks are that they peak at peak cooling or peak heating. I showed actually heating up here, so that was a heating example, but peak cooling in the summertime, and which is actually sort of later on in the day around this time period would be a summer peak. A conventional air system is actually sized, so it's I'm not going to say oversized, but it's a large size to meet the peak, right? So it has to be a large system, and a large system costs a lot of money, right? And also its efficiency is low, because its efficiency is the lowest when it's running the most, right? So it's going to have the lowest efficiencies when it's needed. So these are all sort of disadvantages of a conventional operation. So let's take a look at what. All right, we're back. Let's look at what this conventional operation looks like. So this conventional operation would sort of look like this. If we had load this way, the load in, say, the kilowatts load, and this is your time of day. And we're going to look at one day, okay? So this is going to be noon here. We're going to put noon here. And this is going to be midnight. And this is going to be 11 p.m. All right. Let's say sort of 7 a.m. is here. All right, to give you perspective, 5 p.m., sort of when a lot of people go home from work is here, right? So your conventional air conditioning system that, again, is sized pretty large, right? Our building loads, from midnight to about 8 a.m. before sort of, people come into work or our, plant operations start up, then, our peak load, our building load is going to be around like this. And then people are going to come into work sort of at 8 a.m. And then the building load is going to be raised significantly at that point, and increases a little bit slower, but and then at noon it's going to get hot, right? Because we have some solar energy. And then people, we're running some AC at peak here because we have solar and we have occupants, and they're wanting to keep cool. And it's going to be like that until they go home at 5 p.m. And then there aren't as many people there anymore, right? And then it's going to kind of go down like this. So if I were to sort of Pareto all of our loads in here, this is what it would look like. This was what our load profile would look like in a conventional air conditioning system. And now that's our load profile. So on purple, it's our load profile. So in order to do this type of cooling, I would buy a chiller. I would buy a chiller, and my chiller would have to operate at, this is 250 kilowatts. This is 750 kilowatts in this example, and this is 1000 kilowatts in this example. I'm going to run my chiller not very much right now, right? So, my chiller has a large compressor in it, and whatever type of compressor that I have in there, a radial compressor, a screw type compressor, etc. I'm not running that compressor very much, right? I could have bought a smaller chiller, but no, I couldn't have bought a smaller chiller because I'm actually going to, I'm going to need to ramp up to actually 750 kilowatts. And then I'm going to ramp up again, and I'm going to have to produce this much. So, and then I can ramp my chiller back down. I don't want to over chill. I can ramp my chiller back down again. I don't want to over chill again, right? So this is my chiller. And this is underutilized. This is at capacity. When it is at its capacity, it is operating with the least efficiency sometimes. Sometimes the depends on the curve, right? But here our peak chiller load is 1000 kilowatts, right? That's a big chiller I had to buy, but most of the time I'm running it under capacity, but I had to buy that, right? All right, so now if we are going to combine conventional air conditioning with some storage, let's combine some conventional air conditioning with storage, okay? Let's see, let's do green. Combine conventional air conditioning with thermal energy storage. Let's do that now, and let's see how we can change this. What we're going to do is we're still going to have conventional air conditioning. We will still have a chiller, but it will be smaller. We will use the storage for peaks. Okay. And inside that storage, what are we storing? We are storing ice or water. It's a ice or water storage medium. And in this way, I don't have to use my chiller for the peak. It can be smaller, not at peak, right? And then we can operate that chiller at night. Okay, we can operate chiller at night. Are your occupants going to feel that chiller at night? No. What's going to feel the chiller at night? The ice. Use the chiller to cool the ice. It's going to be cold outside. If it's cold outside, that means there is a smaller delta T. If there's a smaller delta T, that means there's going to be an increase of efficiency. Actually, that's why this chiller operates at lower efficiency here, is because the delta T is very high. The temperature between ambient air temperature and outside air temperature is very high. So let's operate this chiller at nighttime. Let's not put it into our facility where our occupants are. Let's actually put it into some ice. And let's take out our ice. Let's take out our ice at this time, at this peak time. All right. So let's see what that looks like. So let's look at this building load again. Let's do the same thing with this building load. Here's our time, and here's our load. Time throughout the day with noon in the middle again. And of course, we have the same occupants, right? We have the same occupants who are going to come in at about 8 a.m. And then they're going to require about 750. And we were sitting at about 250 off hours. And then our load profile goes all the way up to 1,000. And then it goes down again to 750 again. And then at in those evening hours, we're here at around 500. And if I look at the area under these curves, now let's look at the area under these curves and see how much actual energy that is. So this here is power, right? This is power in watts or kilowatts in this case. This is time, right? Power is energy over time. So energy over time got us power. So therefore, if I want to know how much energy is used in this amount of time, then I would just go power times time to get the amount of energy. So if I go 250 kilowatts times how many hours are here, this is 8 hours in the day because this is midnight. Then that's 2,000 kilowatt hours, which is energy, right? Kilowatt hours is equivalent to energy or energy measured in joules or BTU. It's a quantity of heat energy, or it's a quantity of energy that we have to take out of the air. Now, if I were to look at this rectangle of time, again, this one is 750 kilowatts times 4 hours, which would be 3,000 kilowatt hours. This one, this block of time is going to be 4,000 kilowatt hours. And this block of time ends up being 3,000 kilowatt hours. Stick with me here. It will make sense. We are almost at the point of thermal energy storage, but we are not quite there yet. Remember, this is energy plus this energy, plus this energy, plus this energy, plus this energy, all has to be accounted for. Remember, this is a building load. So really, this is how much cooling we need to do. This is how much heat energy. Heat is a form of energy. This is how much heat energy has to be removed from the building. We did not change the building. We did not change the occupants. We did not change the temperature outside. This amount, this quantity plus this quantity, etc., has to be removed from the building. We're not changing science. We're not changing physics. How do we remove this heat from the building? All right. So there are a couple of ways to do this. There is called load shifting and load leveling. All right, so a load leveling idea gives a constant load so that you can buy a smaller chiller. And load shifting gives you even more savings. So how do we solve this problem with ice? Let me write down those two ways. Solve it with ice. Solve it with ice. You either do load leveling or load shifting. Load leveling is pretty good. It's going to make you buy a smaller chiller. Load shifting is even better. That's a happier smile. Okay, so here's what we have to do is we're going to, for load leveling, I will do in blue here. Load leveling, we are going to partially shift the AC load to off-peak hours. And we're going to run this chiller at a constant load. All right. We are going to run a chiller at a constant load, and it's going to be a little over 500. And this is called load shifting. Load shifting. Oh, sorry, load leveling. This is load leveling. So what we're going to do in load leveling, blue, load leveling, is we're going to say, all I needed is this quantity, the area under the curve. So if I get rid of this, plus this, and I can get the same amount of energy, the same bucket of energy by adding this plus this. So I have leveled out all of this to be here and to be here. Then I have offset the same building load. I have taken the same number of BTUs or kilowatt hours or joules of energy out of the system. But I had to run a chiller way up here. I had to run a chiller way up here. So this is my new chiller. This is my new chiller. Am I happy with this new chiller? How big is this new chiller? Let's see, how big is my new chiller? If I did all of these calculations, then I would see it's actually 583 kilowatt chiller. So new chiller is a 583 kilowatt capacity. That is a smaller capacity than we had before. What was our chiller looking like before? I think it was orange. So it is smaller than 1,000 kilowatt, right? It's smaller than the 1,000 kilowatt one. And this is load leveling. But you say, wait a second, how can you do that? That makes no sense. This is wrong. How can you do that? Why are you running this chiller when nobody is there? Why are you running it when nobody is there? In this time, you are running your chiller because look at my chiller. It's this blue line. You just keep running it, keep running it, keep running it. Is it better for your chiller? Absolutely. There's no maintenance of a chiller, you know, starting up and slowing down. You are running it at a constant capacity. You can probably run it at its peak efficiency because remember, a chiller is just a compressor, right? So buy one where you're, you know, that 783 kilowatts is its peak, is at its optimum performance, and you know, run it at its peak efficiency. And I'm going to run it and I'm going to store the energy, store the coldness. Basically, I'm going to remove the heat energy from water or ice. That's what I'm doing here. What am I doing? What am I doing here? I am just meeting this demand with my chiller here, and I'm at noon, I'm just meeting this demand. I'm undersized. That's fine. And now I'm oversized. This chiller is oversized. So again, I'm storing it, or what I'm doing is I'm removing BTUs, I'm removing joules, I'm removing heat energy from ice. And I'm building up the amount of cooling capacity of that ice. So that's what I did with that smaller chiller, and that's called load leveling. Now, we might ask, well, what does that mean? What does that mean to the rest of the times of day? What on earth happens to my occupants in here? Well, what happens to my occupants in here is that they are going to now be cooled by running water from the chiller of the ice. So now your ice is cooling, your ice is cooling, your ice is cooling. How do you do that? Well, the thermal energy storage just looks like a giant bucket of ice. It's a massive building full of ice. It's an ice bucket. Run some cold ice water through our through our air exchangers from our ice water. So we made our water really chilled. We made our ice water chilled in here. In all this time we invested in making all of this chilled ice. Here's our chilled ice. And we did it all for this time of day, this time of day, this time of day. How did we do it? We did it all with a smaller chiller, and that's load leveling. So that's how thermal energy storage is used in a load leveling context. However, we can also do load shifting. So if I take the same scenario and I look at what load shifting is. Load shifting in a thermal energy storage, we're going to write in a special new color. I guess we will use purple. Load shifting has actually even more potential for saving energy. So let's just look at that same example where we have a load in kilowatts and we have time of day here, and we have noon, and we have a situation where people don't work at night. Like many places, they come in at around 8 o'clock in the morning, and then they some cooling is required. All of the equipment's working and everything. It's the same load profile as we looked at earlier for load shifting and for conventional air conditioning. So I'm drawing that load situation again, where this is 11 p.m. This is midnight, and this was 250 kilowatts. This is around 750 kilowatts, and we were peaking at 1,000, and we had to buy a chiller at 1,000 kilowatt chiller for a conventional air conditioning system, but we're just looking at ways of using thermal energy storage to shift some of this now. So that's what our building load is. And let's look in purple here about a load shifting situation with thermal energy storage. So in the case of load shifting, I again have to calculate area under the curve, and then area under the curve, and area under the curve. And in this case, what I'm going to do is I'm going to calculate this as this is sort of our peak. It's our peak and then some. You can do the calculations and try to optimize the calculations. And what I'm going to say is that I'm going to buy a chiller that can operate at a capacity that is a little bit higher than our load leveling. So this was a chiller. How big was this chiller? This was 583 kilowatt capacity chiller, pretty small. I bought a smaller chiller here, right? This one is going to be a little bit bigger. Let's see. This one is going to be, and we would have to calculate how much. So I'm going to look at this peak period here, and this peak period, I'm going to say that this is 8. So on my chart, this is 8 p.m. Sorry, this is noon to 8 p.m. Okay. And through noon to 8 p.m., I need to know how many total kilowatt hours there are inside that peak period. And the total kilowatt hours inside that peak period, if I were to calculate the area under the curve, it's just the power times the time, right? The area under this curve would be power in load times time. So if I did that, I would see it's 14,000 kilowatt hours. And if I look at that as a ratio of the rest of the hours, okay, rest of the hours, then, or the hours outside of the peak. How many hours do we have outside of the peak? We have about 16 hours left outside of the peak. So what I would need is that same amount. I would need 14,000 kilowatt hours over 16 hours. If I want to turn this off in the peak, if I wanted to produce that much at a different time, not in the peak. So I want to produce this much in order for the peak to be satisfied. Produce this much. But I want to do it in off-peak times. In this time. I want to produce this much, but I want to do it off peak. I want to do it in here. These are my happy hours here. I want to do it here, and I want to do it here. I don't want to do anything in here. I do not like this time of day. This time of day is peak. I don't want to ask the utility to give me any power in that time. They charge me lots and lots of money in peak. I want to do what's called peak shaving or peak savings or peak shaving. I want to shave off my peak. I'm shaving off this peak. As far as the utility company goes, I don't use a lot of power. I certainly don't use it at midday. That's embarrassing. So I installed this nice system because we're all doing our part. And I know that in order to be able to make the amount that I will need to use, because I don't have that peak anymore, and I'm not asking for this power anymore, I'm going to have to make 870. I'm going to have an 875 kilowatt compressor or chiller. So the 875 kilowatt chiller then is here. Let's just kind of choose another purple for it. This would be my 875. My 875 kilowatt compressor is going to work when I'm happy for it to work. Here it goes working. And then I'm going to work it down here at 0 power. All right, see this? And then I'm going to work it again, but I'm not going to vary this compressor. It's going to be on off because I actually need this area under the curve. Okay, so my compressor is on. Oops. My compressor is on. My compressor, my new compressor that I bought is off. My compressor is on again. Let's look at the area under this compressor curve. Area under the compressor curve looks like this. What would this total? This would total 875. And the trick is here, we're not playing with physics here. This makes sense because the trick is my compressor went to make some happy people here, but my compressor went to chill water here. So I'm removing heat energy. So I am storing. I am chilling. Really, technically, I'm removing BTUs from ice. Here, I'm doing some work for my occupants. but I'm doing some work for my ice. I'm doing some work for my occupants. I'm doing lots of work for my ice here. And how do we get that chilling done? And we are not asking the utility company for anything. We are not asking the utility company for anything. It's coming from ice, which is kind of free, right? Our ice essentially, literally, is a giant ice bucket that sits on our facility. Here's a person with a happy smile on their face saying, I have a giant bucket of ice, or it's actually like a sludgy water type of thing. And I am taking some lines and I'm putting them in my heat exchangers in my building, and they are pulling in heat energy, Q in. And that's what does the cooling, like a giant ice bucket. And that's what is happening in this peak period. And you ask the utility company for nothing. That's called load shifting. And the fact that you now have an 875 kilowatt compressor, it's smaller than 1,000 kilowatt compressor you used to have, but you're also turning it off. You're turning it on and you're turning it off again. And because you're turning it off again, it saves lots and lots of money. So this is an excellent energy savings opportunity for peak load shifting.